So today we're going to talk about VSEPR theory, and VSEPR stands for valence shell electron pair repulsion, or VSEPR theory. So what it is a three-dimensional model used for arranging electron pairs since they repel one another in space. Remember that electrons, they carry a charge, they have a negative charge, which means that if you put them together, their natural tendency is to repel one another. So it is used, VSEPR theory is used to draw molecular structures so that we know their correct orientation in three-dimensional space. We also use Lewis diagrams to figure out what structures look like, but there is a fundamental flaw that's associated with a Lewis diagram. Lewis diagrams don't tell us what the correct molecular arrangement is and how molecules actually look in three-dimensional space. So VSEPR theory is designed to help us figure out how molecules actually look in three-dimensional space. So I started off with a table, and we're just going to go through the different bonding clouds, a general structure, what are the examples, what the molecules actually look like, the shapes that they take on and what those shapes are actually called, and the bond angles. So at first we're going to start off with the simplest molecules, and those are the ones that have no electron pairs. And these are the framework and the basis of VSEPR theory. So the first thing that we're looking at is if you have one bonding cloud. So if you have one bonding cloud, the general formula for any molecule at this point is AX. A stands for the central atom, and X stands for any atom that is bonded to the central atom. So we have an example, and our example is hydrogen, a hydrogen molecule. If you draw it as the Lewis diagram that we know of, which is still useful, we still use it, we'll take the one H as our central atom, and the other X is the H bonded to the central atom. This shape is linear, and its bond angle is 180 degrees. Okay, moving on. Two bonding clouds. We have one central atom, two atoms bonded to the central atom. Real life example is carbon dioxide, CO2. Its Lewis diagram looks like this, but it's also the correct VSEPR shape. And it is also linear, and it is also 180 degrees. The next one involves three bonding clouds this time. And the bonding clouds are actually the hybrid orbitals, which we'll learn about in another lecture. But we'll start off with the table right now to make things easy. In three bonding clouds, again, we have A as our one central atom, and then we have three different atoms bonded to the central atom. A real-life example would be boron trifluoride, BF3. And BF3, if you were to draw the Lewis structure, let me just erase these with my crude eraser, which is my finger. BF3 actually looks like this in the VSEPR model. If you were to draw BF3 as a Lewis diagram, you'd probably end up doing something like this. Sorry about that. BF3 as a Lewis diagram would end up looking like something like this. This is not the correct shape. This doesn't tell us anything about its three-dimensional shape. So the correct three-dimensional shape, you draw the three atoms in three different directions. This shape is called a trigonal planar, and its bond angle through all of them is actually 120 degrees. So students are expected to memorize these. At this point, you should be able to recognize that this is trigonal planar, and it has 120 degrees. These are linear, and they're 180. Okay? Oh, sorry, wrong board. Okay, moving up. When we have 4 bonding clouds or 4 different hybrid orbitals, our general structure is AX4. So you have 4 different atoms that are bonded to A, which is the central atom. For an example, CH4 being methane, and carbon is your central atom, and your hydrogens point in 4 different directions, and this structure is called a tetrahedron. So it takes on a tetrahedral shape. So if I'm to draw my carbon and my hydrogens, what this actually means, this bolded bond right here shows that the hydrogen is pointing out from the board, and it's almost pointing directly at my face. This hashed bond shows that that hydrogen is pointing to the back of the blackboard. And by drawing the bond this way, you're actually showing, in a 2-dimensional diagram, you're showing that there is a 3-dimensional shape. Okay? Moving on to 5 electron clouds, 5 different hybrid orbitals. Your general structure is AX5. 5 atoms bonded to the central atom. Phosphorus pentachloride, PCl5 is your example. And the actual structure, bear with me here. This chloride, for example, again with the bolded bond, is facing outwards, and this chloride with the hashed bond is pointing to the back of the board. This shape is called trigonal bipyramidal. The axial bond, which is this chlorine compared to this chlorine, this is called the axial bond, and that bond angle is 180 degrees. The equatorial bonds they range this one to this one, or that one to that one. They're both 120 degrees. The six different electron clouds, again, now 6 different atoms bonded to the central atom. The central atom, by convention, we usually write first. The other atoms are then bonded to the central atom. Sulfur hexafluoride is an example. And this shape, you see the 2 fluorines are pointing towards us. These 2 back fluorines are pointing to the back of the board. This shape is called octahedral. And this is also coordinatively saturated. It means that it can't take on any more bonds. 6 is the max. Don't get confused with the octa part of octahedral. A common misconception is because octa usually means 8. Students think that there are actually 8 bonds, but there aren't 8 bonds, there are 6. Okay, so we'll have to move on to the next board to continue on with the rest of the compounds that we're now introducing lone pairs. Okay, so now we're continuing on. We're going to take VSEPR and we're going to kick it up a notch. We're going to make it more difficult because that's what chemists love to do. They love to take a simple theory and make it even more complicated. But I'm going to try to explain it so that it doesn't seem as complex, so that you remember when you're looking at these, all of these are still connected to the same thing that we talked about previously. Okay, so one very important feature, if we have molecules that have lone pairs, when you have a non-bonding pair, which is another word for lone pair, of electrons, the non-bonding pairs will affect the shape of the molecule. And the reason for that is because, again, they're charged, and if you're forcing charged species together, naturally they're going to want to repel one another. So in my general formula example, I represent electron lone pairs as the letter E. So we're going to go back to the simplest bonding cloud. And again, we're going back and we're talking about having a compound having only two hybrid orbitals. Its general formula now is AXE. A is still the central atom. X is an atom bonded to the central atom. And E is your one electron pair. So an example of that could be the nitrogen molecule. So I have to designate one as my central atom. Even though they're equivalent, I'm still designating the one nitrogen as being my central atom. And in red, I did its one lone pair. That represents the E. And the other end from the nitrogen molecule, which has black lone pairs, is my X. So it still follows this formula even though they are essentially equivalent. This compound is also linear, and it definitely still has a 180-degree angle. 3 bonding clouds now, 3 hybrid orbitals. My compound now, AXE2, which means that it will have 2 lone pairs of electrons. An example of that would be oxygen. And oxygen, I'm going to pretend that the left one is my central atom. It has its 2 lone pairs, and even though it's equivalent to the other guy, this other oxygen on the right side is acting like my X, right? It is bonded to the central atom. It is also linear, and it also has a 180-degree bond angle. 4 electron clouds.
Would members of the AV club please come to the main office?
Okay, 4 bonding clouds, AXE3, 3 lone pairs. An example is fluorine. So this fluorine is my central atom. This is my X bonded to the central atom, and he's got 3 lone pairs. Still linear, and still 180 degrees bond angle. Okay, so now I'll have to move on to the next board. This time, 4 bonding clouds, 4 hybrid orbitals. AX2E2, meaning 2 atoms bonded to A, which is my central atom, and 2 lone pairs of electrons. An example is water. Normally you would imagine seeing water drawn this way because water is special, we draw it the other way, but it should be drawn backwards to show that O is really the central atom, and the hydrogens are the atoms bonded to the central atom. Just keep that in mind with water. Water is really special. Its shape is very much like a tetrahedron. So it's just like CH4, but only this time you have 2 lone pairs of electrons have been substituted from having the bonds. This, if you you were to actually build this structure, you wouldn't see these lone pairs. You know they exist because there are 4 different hybrid orbitals, but when you actually build the 3-dimensional shape, it looks bent or angular. So that's why we call it bent or angular. It's still tetrahedral, but having the lone pairs there changes the actual shape of it, so it changes the molecular geometry. The electron geometry is still the same, it's still tetrahedral. But the name of the shape now changes, it's called bent or angular. The bond angle has also changed. A tetrahedral bond angle is 109.5, which is really important to know and memorize. Why it actually changes? Well, it's because you have these 2 lone pairs of electrons. They don't want to be near each other, so they want to repel each other as much as possible. The act of them actually repelling one another pushes these guys closer to each other, and that's why the bond angle changed from 109.5 in a tetrahedral structure to 104.5 if there are lone pairs now which repel one another and push bonds closer to one another. Another example, still 4 bonding clouds, 4 hybrid orbitals, this time only 1 lone pair. An example of that is ammonia. Ammonia, as you can see, still has the tetrahedral shape, but now I put one lone pair into one of the hybrid non-bonding orbitals. Sorry, not a hybrid, that's the non-bonding orbital. It would look like a normal tetrahedral shape if that lone pair wasn't there, but there is. Now, if you were to build this structure, that lone pair is actually missing, you don't see it, and the actual geometry, the actual molecular geometry of the compound, we call a trigonal pyramid. And its bond angle changes from a tetrahedron, which is 109.5, to 105.3. And something that is worth noting here, if you have 2 lone pairs, there's a greater act of repulsion, that bond angle changed more. It's actually lower, a lot lower than if there is only 1 lone pair. The 1 lone pair doesn't repel the rest of the bonds from each other as much as 2 lone pairs do. And that's why the bond angle is only 105.3 versus 109.5 versus 104.5. That's a question that you may be asked on a test. It's really important to realize that. Don't forget that it is electron pair repulsion theory. Okay? 5 different bonding orbitals. AX4E this time, 1 lone pair of electrons. An example, real life example is sulfur tetrafluoride. 1 lone pair. And now, same thing, this 1 lone pair pushes the rest of these bonds towards one another, and the axial bond in a normal trigonal bipyramid, where there isn't a lone pair, the axial bond is exactly 180 degrees. The equatorial bond is exactly 120. That 1 lone pair pushes everything close together, and it distorts the actual bond angles. So if you were to build this actual shape, this would look like a seesaw that is halfway up. So we call that a seesaw. Another one that has 5 electron clouds, or 5 bonding clouds, 3 bonded atoms, 2 lone pairs. Real life example is IF3. The 2 lone pairs repel one another. If you were to build that actual shape, it looks like a T-shaped structure. So it kind of looks like an upside down T. And those bond angles are 90 degrees to one another. The next one has 3 lone pairs, and an example is Xenon Difluoride. Xenon, you remember, is a noble gas. It used to be called an inert gas until these xenon compounds were actually found in nature, and the name changed from inert gases, inert means non-reactive, to noble gases because, well, xenon actually reacts and makes compounds. This time, this should be, normally if there were bonds here, this would be the trigonal bipyramid. But because those are missing, now they're lone pairs. If you're to build this structure, it looks like it's linear because you can't actually see the non-bonding lone pairs. And its bond angle is 180. But still, the electron geometry is a trigonal bipyramid. The molecular geometry is linear. Molecular geometry is what it actually looks like. The next one, having six electron clouds, 5 bonds, 5 different atoms bonded to the central atom, one lone pair, ICl5 is an example. This should be a regular octahedron, so it should be octahedral. Its electron geometry is octahedral, but the presence of this lone pair, once you build that structure and you see what it actually looks like, it doesn't exist, so we call that square pyramidal. And its bond angles are actually less than 90 degrees. If now you remove one of the atoms and you put 2 lone pairs of electrons, such as in Xenon Tetrafluoride, AX4E2, E for 2 different lone pairs, the structure, if you actually build it, you don't see the lone pairs, so it looks like a square, and we call that square planar, and its bond angle is 90 degrees.
Just a quick question. What happens to the bond angles in the square planar molecule? Because there's 2 lone pairs, would it affect any bond angles?
Those ones don't affect the bond angles. You don't even see them when you actually build the structure.
So they actually cancel out?
They cancel each other out.